Okay, welcome to another edition of Mr. Weis Solves an Old AP Problem. Today we have calculus problem from 2015, number 4. This problem is all about a differential equation, which it's going to ask you to do various things. One of the things it's not going to ask you to do, interestingly, is solve the differential equation. Here is the differential equation. Our deal is that we have some function, y is some function of x, and we know that its derivative is always equal to 2x minus itself. We're trying to deal with such a function, or maybe there's many such functions. Likely there's many such functions. We're not actually going to solve this differential equation, though, because you might recognize that it is not a separable differential equation, which is essentially the only ones we know how to do. Okay, so what does part A ask us to do? Part A asks us to create the slope field for this differential equation at the 6 points that are indicated, and they give us a nice axis to work with. So basically we just want to find it at 6 points. So let's go ahead and do that. Note that this point right here is the point 0, 2. So if I plug in and find out what dy dx is at 0, 2, I find out that the answer is -2. So my goal right now is to kind of draw a slope that is negative and seems to have a slope of 2. So -1 would kind of go like this. -2, on the other hand, is a little bit steeper. So I'm going to draw something that looks like that. Okay, this is the point 1, 2. dy dx at 1, 2 ends up equaling 2 minus 2, which is 0. That's very easy to draw. That's a flat line that looks something like this. This is the point 1, 1. dy dx at 1, 1 is equal to 2 minus 1, which is 1. So I'm going to try to do my best to draw a slope of 1, which looks, I don't know, something like that. This right here is the point 0, 1. dy dx at 0, 1 is 0 minus 1, or -1. A little less steep than this one. I'm going to draw something that kind of looks like this. Okay, this point down here is 0, -1. dy dx at 0, -1 happens to be 0 minus -1, otherwise known as +1. So I'm going to try to draw a similar slope as what I see there, something like that. And finally, this is the point 1, -1. dy dx at the point 1, -1 happens to be 2 minus -1, otherwise known as 3. So this one's going to be rather steep. I want to make it steeper even than this, so I'm going to go something like that. And I think this is a pretty good answer to the first question. To do part B of the AP Calculus BC 2015, number 4. As you recall, with part A, we are working with this differential equation, not a separable differential equation of the form dy dx equals 2x minus y. Again, what this means is solving this equation or looking at this equation means that you're dealing with a function, y equals f of x, or any function, y equals f of x, that happens to have the property that its first derivative is equal to 2x minus itself. Part B asks us to look at what the second derivative of such a function would look like, or what it would be like. It wants us to figure out what d squared y dx squared is. And it wants us to use that to figure out what the concavity of any solution curve to this differential equation would have to be in quadrant 2. So here we go, we're going to use implicit differentiation to take the derivative with respect to x. The derivative of the left-hand side is literally this. The derivative of the right-hand side is the derivative with respect to x of 2x is 2, minus the derivative with respect to y. Well, I don't know what y is, so we just say dy dx. And even though I don't know what y is, I do happen to know what dy dx is. It's literally the original differential equation. So we have 2 minus 2x minus y, which gives us 2 minus 2x plus y. Now, imagine that I am a solution to this differential equation somewhere in quadrant 2. Imagine I'm a solution. I have no idea what the solutions to this look like. We did a little bit of a slope field to give us kind of a sense of what the curve might have to look like over here, mostly in quadrant 1 and a little bit in quadrant 4, but we didn't really analyze it at all in quadrant 2. But imagine that I'm some solution curve over here. So I'm at some point right here, and I'm some solution curve that goes through that point. Well, what would I know about that point? I know that it's, let's give it actually a name. Let's say that it goes through the point A, comma, B. So imagine a solution to this differential equation passes through A, comma, B in the second quadrant there. Well, then what do you know? You would know that the second derivative of that point at A, comma, B would equal 2 minus 2A plus B. But note, B is positive, but A is negative. So d squared y dx squared at this point A, comma, B would end up equaling 2 minus 2a. A's negative, so this part right here is positive, plus b, which is also positive. So all of this is positive, and we now know that, I don't know what it looks like, but I can tell you that it's definitely concave up. I don't know if it's increasing or decreasing at that point, but it's definitely concave up. And this will be true of any part of the solution, of a solution curve to this differential equation while it lives in the second quadrant. We're on the third part of the AP Calculus BC 2015 number 4. Still looking at this differential equation dy dx equals 2x minus y. For part C, it says, imagine that y equals f of x is an actual solution to this. And not just any solution, because remember, there are likely infinitely many solutions to this. But let's let it be what's called a particular solution, the one that happens to go through the point 2, 3. This is kind of like what would happen if we were given some initial value problem. This function would be a solution, the solution to that initial value problem. We can't do that because we can't actually solve this differential equation, but that's the idea. And it asks us, would f have a relative min, relative min, max, or neither at the point 2, 3. That's what it would ask. Okay, well, let's try to figure it out. So first of all, in order for it to have a min or max at all, 2, 3 would have to be a critical point, or x equals 2 would have to be a critical point for this function. So let's see if x equals 2 is a critical point. So first question, is x equal to a critical point? Well, in order to figure that out, we have to look at dy dx at the point 2 when x is 2. When x is 2, y happens to equal 3. So let's see what we get when we do that. Since we happen to know what dy dx is, we can plug in, and we're getting 4 minus 3, which is 1. So the answer is no. The answer is no. Thus, the answer is neither. Thus, no relative max or min there. And we're done. That was actually really easy. I wasn't expecting that. I thought this was going to end up equaling 0, and then we were going to have to use maybe the second derivative test to decide if what was happening at that point was a concave up or concave down, but it's actually easier than that. Favorite part of this problem. We're now going to do part D, I believe we are on. Again, of the 2015 number 4, we're dealing with this differential equation that we can't solve. Part D asks the coolest question, though. It says, I wonder, though, we can't solve this generally, but here's a question. Are there any functions of the form y equals mx plus b, which are the solution of this differential equation, which solve this? And this often happens, actually. Often when we solve a differential equation, we get a whole family of solutions. And often that family of solutions, the curves all look kind of similar, but usually among those curves is like a line or something, or a line or two, that ends up also being the solution to it. So it's an interesting question. Are there any lines that solve this? Well, let's see. If y equals mx plus b solved it, was a solution, what would that mean? Well, that means it would have to satisfy this differential equation. It would have to make this differential equation true. This would have to be true as functions. So let's see what we would get. That would mean was the solution, so that would mean I could plug in, and on the left-hand side I'd get dy dx, but dy is just mx plus b. So on the left-hand side I'd get m. On the right-hand side I'd get 2x minus y, but y is mx plus b. So I'd get the equation m has to equal, I'm going to do a little bit of work here, let's see, 2 minus m times x minus b. Now it's a little bit weird to think about what this is saying. Remember, this equation here is an equation that's setting equal two functions. On the left-hand side, we have the function which is the derivative. This is a function. And on the right-hand side, we have this other function over here. Whatever y is, the function on the right-hand side is 2x minus y. If y happened to be x squared, then the function on the right-hand side would be 2x minus x squared. This is a function. And I'm trying to find any function of this form that happens to make this equation true. Well, what does it mean for two functions to be equal? It's a lot different than what it means for two numbers to be equal. For two numbers to be equal, you just look at them. Are they the same number? Sometimes you have to simplify one of the numbers so that it looks like the other. It can maybe not be obvious that two numbers are the same, but ultimately asking if two numbers are the same is a simple question. Are they the same number or not? Two functions being the same, though, is much more. Two functions are the same if, given any input value, x value, if you plug it into either function, you always get the same y value. So, these two functions have to be equal, but because we're trying to solve this for a linear function, the left-hand side of this is just a constant, because the derivative of a line is a constant, it's namely the slope. So if these two things are going to be functions, they have to be equal for all x. Must be equal for all x. So when I plug in x equals 2, this has to be true. When I plug in x equals -1, this has to be true. But on the left-hand side, we have a constant. The only way that's going to be true for all x is if this thing right here has to go away, so that when I plug in x, nothing actually happens. So from this, we can realize, thus, 2 minus m has to equal 0. Otherwise, I'm going to get different answers on the right-hand side of this equation for different x values, and yet on the left I see it's always supposed to be a constant. So from that, we find out that m has to equal 2. But now, if I plug back in here m equaling 2, look at what we get. We get that 2 equals -b. In other words, b equals -2. And I believe we have found now all solutions. The answer is any line of the form y equals 2x minus 2 will make this true. And you can check. The derivative of this, that's the left-hand side, is 2. And on the right hand side you'd have 2x minus 2x minus 2, 2 equals 2. That's our only solution. Very cool problem. This part, this reasoning, is some deep stuff actually, and is very, very cool.